Hello everybody, this video is going to be about rate laws. We did learn a little bit about rate laws in Honors Chem. You learned how to write what are called differential rate laws. We'll review that a little bit, and then we're going to learn how to do what are called integrated rate laws, and we're going to see how we can graph some of this data to help us determine the reaction orders. So a differential rate law is the kind that you're probably used to seeing. They talk about the relationship between concentration and the rate. So we call that typically just the rate law, but really it's a differential rate law. And so when I'm trying to see how the rate changes when I double or triple the concentration, that's a differential rate law. Sometimes we want to figure out the relationship between the concentration and the time that has passed. That is an integrated rate law. That's the new kind that we'll learn about today. The really important thing to understand about rate laws is that they must be determined experimentally. This is not something you can just figure out by looking at a chemical equation. This is something that you have to actually perform an experiment on, so they're very data-heavy problems. You'll have data charts and graphs and things like that to look at. We'll have the concentration raised to some power. That's what you learned to do in Honors Chem, is look at those data charts and figure out what exponents that needed to be present. We have the rate equal to some kind of a rate constant. Make sure you use a lowercase k. A capital K is for equilibrium, right? This is a lowercase k. We have our concentrations of our reactants, and they're raised to what we call the orders, the exponents. Remember that the products don't appear in this. It's just the reactants. We are just trying to determine the rate based on how those reactants are colliding. The way we talk about it is we say that the exponent is the order with respect to A, or the order with respect to B. If I want to know the overall order for the entire reaction, the overall order, I add those exponents together, and that gives me the total order. If our reaction occurs in a single step, then the coefficients in the balanced equation will match the orders. But that is not common. It is rare that a reaction happens in a single step. It is much more common for them to take multiple steps. And in that case, the orders are not going to match the overall coefficients. So for example, this reaction does occur in a single step. So when I look at the rate law, I will notice that the order matches the coefficient for each chemical. We say that it is second order with respect to nitrogen monoxide, and that it's first order with respect to the oxygen. Overall, I would add those numbers together, and we find out it's third order overall. That only works when it's a single step. When it's a multiple step, or we don't know how many steps it takes place in, we have to use something called the method of initial rates. And so what we're going to do here is we're going to systematically change the concentrations of our reactants while holding some other concentrations the same. We're trying to basically control how many things are changing at once. That allows us to see how the rate changes based on changing one single reactant. And then that tells us what our exponents would be. You hold everything except one constant, you change that one, and you see what the rate does. It might go up, it might go down, it might not change at all. This is what we practiced a lot in Honors Chem. Do you remember you'd have a chart like this? And we would have to use the method of initial rates to figure out what the orders were. I know that my rate law is going to be rate equals K times the concentration of this raised to some number times the concentration of this raised to some number. And I'm trying to find out what those exponents are. So we have some kind of generic one like this. I'm going to look at my data table and I'm going to say, okay, let's change the concentration of nitrogen monoxide while holding this one constant. So if I look here, this doesn't change. But what happens to the concentration? The concentration doubles. What happened to your rate? When you double the concentration of nitrogen monoxide while holding the other chemical, the chlorine, constant, you can see that your rate quadruples. So if I double my concentration, but my rate quadrupled, that means that my exponent must be a 2. Because 2 to the second is 4. It's changing my rate by a factor of 4. Change in concentration doubled, rate quadrupled, therefore the order must be second order. Now we can try to figure out the other one. So if I look, experiments 1 and 3 were used because this is held constant and now this doubles. And what happens to my rate when I double the concentration of the chlorine? My rate doubles. So 2 raised to what power equals 2? A 1. It is very possible that you could do these problems with choosing different experiments to compare. You could solve them in different order. You could have figured out the chlorine first and then gone back and figured out the nitrogen monoxide. Sometimes you have to figure out one and then do some funny math to try to figure out the other when it's not so obvious. But we should all get the same answer when we're done. So if you decided to use trials 2 and 4, you should get the same answer as 1 and 3. Now with that said, sometimes because these are experimental values, your numbers aren't perfect. You may not end up with exactly the same thing. You may have to be rounding. If you get a change of 1.94, that's probably a double, right? That's rounding to 2. So you have to be comfortable and have to understand that the experimental data is not always perfect numbers. You have to have a little bit of judgment here. Now, let's try to figure out what the rate constant would be. We have our equation, but we still don't know K. So what I can do is I can take any of the trials, it doesn't matter which one, and I can plug in the concentrations, I can plug in the rate, and the only thing left to solve for would be K. Rearrange. You will notice the units get a little bit of a nightmare, don't they? They get a little bit nasty here. I prefer, personally, instead of writing moles over liters, you should realize you could write a capital M for molarity. That makes it not quite so cluttered. You do have to keep track of the units. If you think about it, concentrations are in molarities. So a molarity squared times another molarity would be right? Raised to the third. Rate is molarity per second. So you can divide molarity per second by molarity to the third, and that's how you end up with these crazy units here. You could also write this as 1 over capital M squared per second. You'll have a reference sheet that walks you through all the combos of the units. Just make sure you don't forget to include those. They do ask about the units here. They like to see that you're actually keeping track. So here's kind of how I like to do it. Rate K M squared, M to the first. I divide to try to isolate K. I see what cancels out, and I'm left with my units. I like doing this off to the side as almost like a little separate problem to figure out the units. I don't like to try to do it all at the same time as finding the actual number, personally. Some people just memorize it. They just memorize, I know exactly what the units are if it's a third order reaction. Great. Sounds good. Okay, I'm too lazy for that. I'd rather scratch it out on my paper. This can be written in many different ways. You could use moles and liters instead of molarity. If you don't want to use fractions, you could use negative exponents. You could use negative exponents while using moles and liters. It doesn't matter. You should be comfortable enough with these units that you would recognize any version. It shouldn't matter if I use a capital M and you use moles per liter, or if I use fractions and you use negative exponents. We should all understand that they're all the same. They'll often ask you for the overall order at the end. Sometimes people get so excited to have finished the problem, getting your K value and your units, they forget to finish it by saying the overall order. Remember, you just add them together. Always make sure you're answering all parts of kinetics questions. They often have many, many parts. If you have a zero order and you change the concentration, there's no change. That means that this chemical is not directly responsible for how fast the reaction is going. It's not participating in whatever the slowest rate determining step is. It's still necessary for the reaction to happen, but it's not dictating the speed. Orders of 1, 2, and 3 are the most common. You may sometimes see a 1.5 or other fractions. You may sometimes see negatives, but those are not very common. Be aware. You should always notice and pay attention, right? Because it may pop up once in a while, but most of them are 0 to 3. If you think about it, we're not going to have orders of 15, because for a reaction to have 15 molecules collide perfectly for a reaction to happen would be bonkers. That has a very low probability of happening. So not something that you're typically going to see. Sometimes we want to use a slightly different type of rate law called an integrated rate law. An integrated rate law is one where we're comparing the concentration and the time that has elapsed. That is a very common one because that's something we can easily graph. It's something we can easily measure with our equipment. So integrated rate laws are very helpful. The math for them is more complicated, which is why we don't learn about them in honors chem. but we will learn about it now. So I have a little mnemonic that I like, a little memory device, CNR. You're going to have 3 types here: 0 order, 1st order, 2nd order. If the change in time is being graphed with concentration and you get a linear plot, that means your reaction was 0 order. If you have to graph the natural logarithm of the concentration to get a linear graph, it's 1st order. If you have to graph 1 over the concentration to get a linear graph, it's 2nd order. So CNR is trying to remind you, is it concentration, is it natural log, or is it reciprocal? 0, 1st, 2nd. So when you graph these things versus time, you are looking to see how close is your plot to that perfect y equals mx plus b. These may look horrible, but if you break it down, you can see here is y, m, x plus b. Y equals mx plus b. Y equals mx plus b. Concentrations, rate constants, time, all of those are things you know. We're just graphing them and making equations out of them. You got to memorize these, okay? Because you have to be able to graph various things or look at graphs, figure out what order they would be, and then you're going to be able to use these equations to figure out things like the rate constant. You're going to be able to find that slope. The other thing we can use these equations for is figuring out the half-life. How long does it take for half of it to be used up? Typically, half-life is talked about with nuclear reactions, but it could be used for a regular reaction. At a particular time, if we're at the half-life, we have half of what we started with. So if you plug that in to a 0 order reaction, instead of saying AT, right, you end up saying that your half-life is your starting concentration divided by 2 times the rate constant. And that will tell you how long it takes for half of your material to have been used up. For 1st order, you end up with 0.693 over your rate constant. Some of you might notice that this number is a special number. That's the natural logarithm of 2. Because we're taking half-life and we have natural logarithms involved for a 1st order, that's why we end up with ln of 2. You could either remember this as ln of 2 or you could just memorize 0.693. It really doesn't matter. For 2nd order, our half-life ends up being 1 over rate constant times our starting concentration. So if you ever want to know how long it takes to use up half, you have to know what order you have. You could use method of initial rates if that's possible, or you could graph your data and do your integrated rate law to figure it out, and then you know which half-life to use. So you should be able to tell me what the rate law is for the orders and what the half-life is for the orders. I'm not going to ask you past this. We're not going to worry about 3s and 4s, etc. We're not going to worry about fractions. We're not going to worry about negatives. Just these ones, because these are the common ones. When you have a zero order reaction, when you lower how much you start with, you're going to get a shorter half-life. A first order reaction is what most of us are used to thinking of. When we have like a nuclear decay reaction, something radioactive is falling apart, stabilizing. It doesn't matter what the concentration is. The half-life is constant. It's not changing based on the concentrations. That's what we consider like a normal half-life. For a second order, it's inversely proportional to how much you start with. So if you start with more, if you start with a higher concentration, your half-life will be shorter. Why these are all true is very complicated. It has to do with the reaction mechanics and things like that. Not something we're going to get into. They just want you to understand that not all half-lives are like what you learn about in nuclear chem. Some half-lives depend on the concentration. Sometimes it speeds it up or it makes it go faster. Sometimes it makes it shorter. So you have to understand that the order is part of this. That's why we're learning about this half-life stuff in kinetics, because it's talking about the speed and how fast and how long it takes to use up half. It's all about the speed of the reaction. So you got to make sure that you have memorized what you would graph and how your straight line plot gives you information about the order. So if you graph A versus time, concentration versus time, and it's straight line, you know it's zero order with respect to A. If you have to graph the natural logarithm versus time, then that's first order. If you have to graph 1 over A to get a straight line, then that's second order. So your graphs may look something like this. Let me show you an example. Does that look very straight to you, that blue line? This is concentration and time. That doesn't look very straight to me. That looks pretty crummy. I don't think this is zero order. This is natural logarithm of the concentration and time. That looks better, but that still doesn't look super straight. I don't think it's going to be first order. When I graph 1 over the concentration, look how straight that is. That tells me this is probably second order. Now, looking at it and saying, oh yeah, that looks pretty straight is not very accurate, right? We should get some kind of a number, some kind of mathematical indicator that this is actually a straight line. So Excel or your graphing calculator can tell you what's called the R-squared value. R-squared is a statistical thing that helps you figure out how good of a fit you have. An R-squared of 1 is perfect. That means it is literally a perfect line. So 0.999, that's pretty close to 1. So you would graph your 3 graphs, you would get your R-squared values, you'd see which one is best, and now you know which order you have. Sometimes you may be given the data like this, and you have to plug it into either a calculator or into Excel. Now, to try to be nice, I made an Excel sheet where you can plug in your data and it will automatically graph your 3 graphs and automatically give you your R-squared values. So you can use that. It should be linked in the PowerPoint. It should also be linked on a reference sheet for you. I hope that's helpful. You don't have to use it. You can do it yourself. You could use your graphing calculator. I've even seen special rate law programs for special models of graphing calculators, just make sure if you're using something that somebody else has made, that you are still making sure your brain is turned on, you're paying attention, you're thinking about what's being graphed. You don't want to rely on someone else's Excel sheet or someone else's program to do all the thinking for you. You need to make sure you're still engaged in what's happening. So, for example, if you were to plug this into your graphing calculator, you get a graph like that. You would tell it to do all the statistics and outspits your R squared. Not so good. Here's the natural logarithm. Well, that's a pretty good R squared. That's not too shabby looking. Ooh, that one doesn't look so straight. Nope. So I think this is first order. I'm pretty sure that's first order. That gave us the best linear plot. So I can now write the rate law. I know that it's going to be rate equals your rate constant times your chemical raised to the first power. If I want the integrated rate law, I would choose the one that matches first order, which is the natural logarithm of your concentration equals negative kT plus natural logarithm of your starting concentration. But if I ask you now to solve for K, that's where people don't know what to do next. They can kind of plug numbers in. They can figure out which row to write down from a chart. But now you have to use the plot line that it gave you, and you got to figure out the slope. Because if you look here, if this is y equals mx plus b, m is my slope right here, right? K is what we're looking for. So my calculator, or you could do it with your data table, you find your slope, your change in concentration, natural logarithm of it over change in time. And if we're looking at our integrated rate law, slope was negative k. Therefore k, it's not negative 8.32, it's positive 8.32 times 10 to the minus 4 per second. Okay. For our first order, oh, sorry, this is just showing that you could have gotten it from your calculator or from Excel. It tells you, remember on calculators in Excel, they will sometimes instead of saying M, they'll say A. Same thing. So for first order, the slope is negative K. And look at what your intercept is. Natural logarithm of your starting amount. For second order, your slope is K. And your intercept is 1 over your starting amount. There are more complicated scenarios where you have integrated rate laws with more than one reactant. And when that starts to happen, when you start getting really complicated things like this, they get really tricky really fast. So what we will often do is we will play a little game with our experiment, and we will try to essentially trick it into pretending like it's more simple. So if we make the concentration, let's say, of B really much bigger than A, and we make C way bigger than A, then when I change B or C, it's not that much of a change compared to A, right? When B and C get used up, their amount is so huge it's not really that much of a difference. Do you remember the 5% rule in equilibrium, where we said compared to what we started with, it really doesn't matter? It's a similar concept here. That will allow us to pretend like the only thing that's changing is A. Now, do you see this little mark here? This little apostrophe? That's telling people that it's kind of fudged. We kind of faked it. We were playing some funny games here because this one up here is way too tricky. So when we do that, we call it a pseudo order. So it would be pseudo first order, or pseudo zero, or pseudo second order. We say it's a pseudo order. We're simplifying it. The prime symbol is telling you it's a pseudo order. Okay, so this is going to be a bit more graphing than we're used to in some of our chapters. There is a bit more math, plugging in numbers to different types of equations. Remember, it's not just like you have one Halflife equation. You have to know what order, because there's multiple options. You have differential rate laws and you have integrated rate laws. But really, all they're doing is the same thing. They're all trying to describe the speed at which these reactions are happening. And they're trying to use that speed to help us figure out the mechanics and the mechanism of how these reactions happen. All right, everybody, that's it. I hope this was helpful. Bye.